Hello, I'm Austin Edler. I'm in Physics 2211, and this is my Lab 3, the mass of a black hole. Hope everyone's having a good week, and the Jackets win the game on Saturday. So, the purpose of this lab is to calculate the mass of a black hole based on the motion of a star, and it's the computational motion. We're doing this using Python, so it will be simulated, but we should be able to analyze how the star moves around the black hole and calculate the mass of the black hole, which is a pretty cool concept. And then the second part, we will use that mass that we previously calculated, and we're going to add another component. We're going to have it a spaceship, and it's going to be flying around, and it's going to cross paths with the black hole. And then we want it to travel. We want to find out the exact speed that the spaceship must travel so that it doesn't get sucked into the black hole. So shouldn't be too hard, but we're going to have to see with the Python. So here's the fundamental physics. The initial conditions are that that the star is in orbit of the black hole and it's in circular motion. And then for the spaceship is just that it's traveling at a horizontal velocity. So the fundamental physics would be that the net force, that's Newton's second law. So net force equals change in momentum over change in time. And also net force equals the force, net force parallel plus net force perpendicular. That's for circular motion. And that'll really come in handy when you combine those two right here, that this could equal this, because then you find the components for the momentum. And also we have the position and velocity update formulas, which are, we've seen these before, they're kinematics, but yeah, that'll be helpful, really helpful for the spaceship one, just to see how, the force is changing and how the velocity will change based off how close it's getting to the black hole. And what that has to do with the force net, that with the black hole is the gravitational force, which we've learned about. Fg equals gmm over r squared times r hat. So that'll play a huge part in our experiment. So here's the first experiment, which is the mass of the black hole. And here's our initial conditions: gravitational constant, mass of the star, and we did the delta T. I did how many seconds in a day? So it's like 60 minutes times 60 seconds times 24 hours. So that's like every second in the day. And then yeah, over here we got the initial velocity, the initial momentum, how much they're changing by. So yeah, we just did a lot of calculations there, which we normally would do on paper, but we're simulating it. And then to find the mass of the black hole, we basically reverse the gravitational formula. So it's like F equals gmm over r squared. So this is big M, little m. So yeah, we did that and then we printed it. So here we go. We got the average mass, we got the net force, and we got both components of the net force. So that's super helpful for the circular motion. Over here we got part 2. This is where we don't want the spaceship to crash. That's why it's called don't crash. So once again we got the initial conditions with the planet mass and the ship mass. And this time I just put the delta T as 1 second just because it's a little bit different when the spaceship's already moving. And down here we've got the other code with the net force on the planet and the ship on the planet. It's really the black hole, but it was just put this planet in the Python code. So yeah, and this is the radius and the gravitational force. So we got all that going on. And then yeah, this is the graphical data. So it did not actually go around and crash in the black hole. It made it out because we found the exact velocity. So that worked out nicely. So some sources of error is obviously this was a computer simulation. Like we didn't take actual data from a spaceship in a black hole. So it won't be super realistic. I mean, it's definitely pretty good, but there could be other asteroids and other planets in the system which are encountering the spaceship as well. So it would change the force of gravity, change the net force. We're only accounting for one point, which is the black hole. So that could be weird. And then also updating the gravity. The force is changing all the time, like every time the radius changes, and we're not really accounting for that. And that would make a difference just because that's part of the equation. And here's the what if and what do you mean. What velocity would you need to enter the orbit? So the spaceship to enter the orbit of the black hole, it would need negative 0.4 times 10 to the negative to the 6 and 1.1 times 10 to the 7. And what's the difference between the components of force and the components of momentum? To calculate force, you need to know systems and surroundings, but to calculate momentum, you only need velocities, mass, and time, so it's a lot more simple momentum. Thank you, everyone. I hope you guys have a great weekend, and yeah.